In this video, we're going to discuss lHopitals rule. lHopitals rule is used in cases where the limit gives us an indeterminate form, either 0 divided by 0 or infinity divided by infinity. In the past, in order to deal with these types of limits, we had to do complicated algebraic manipulations by multiplying by conjugates, rationalizing numerators or denominators, or using special trig limits. We'll now use lHopitals rule from this point on. lHopitals rule is a major theorem, and it gets used all the way through differential equations. This is definitely a theorem that you will want to know extremely well. In order to apply lHopitals rule, you need to understand when it does and does not apply. There are conditions to applying lHopitals rule. Let's look at the definition here. Suppose f and g are differentiable functions over an open interval containing a, except possibly at a. Those are the primary conditions in order to apply lHopitals rule. What do we get when we have a differentiable function? If it's differentiable everywhere except maybe at a, then we know at all the points in the open interval except possibly at a, we know that the function has to be continuous to be able to be drawn without picking up the pencil, because if it's differentiable, then it must be continuous. More than that, we know that there can be no corners or cusps or vertical tangent lines in the open interval except maybe at a. This means that when we look at any particular section of the curve except directly at A, any section of the curve, if you focus in tight enough and zoom in closer and closer, this curve will eventually begin to imitate and look similar to its tangent line, just like we learned in the linear approximation theorem in this chapter. Because this is true, because we can zoom in on the function anywhere except at a, and it becomes over a very short interval similar to its tangent line, we can approximate the function with its tangent line. This means that if we have two functions, f and g, and we're trying to find the limit of their ratio, and it is differentiable so that I can apply lHopitals rule, then the limit of the ratio of f to g will be equal to the limit of the ratio of their derivatives. In other words, I can use their tangent lines to approximate the functions when I'm over this very small interval. This will hold even if the a value is infinity or negative infinity. It also holds for one-sided limits. Let's take a look at an example and see how to apply lHopitals rule. In example 1, we see a limit very similar to one we did in chapter 2. In chapter 2, we would factor the denominator x squared minus a squared into the difference of two squares and cancel the x minus a's. Now that we will have lHopitals rule, we can see whether or not we can apply it, and then we can apply lHopitals rule. When it can be used, lHopitals rule is almost always shorter, faster, and far easier than any algebraic manipulation. To see whether or not you can apply lHopitals rule, you must have one of two what are called indeterminate forms. The first indeterminate form we're going to be looking at is 0 divided by 0. By indeterminate, this word means cannot be determined. In other words, I can't tell yet. Maybe the limit exists, maybe the limit doesn't exist. Maybe it goes to infinity, maybe it goes to negative infinity, maybe it oscillates forever. Indeterminate means the form of the limit cannot be determined directly. You have to do something to it before you can find the limit if it exists. In this case, we will plug in what the limit is approaching, which in this case is a, to see what we get. When we're looking at this a, we'll plug it in place of the x here. This would give me a minus a divided by a squared minus a squared. Plugging that in gives me the indeterminate form 0 over 0. On the test, I will be looking to see, did you plug in what the limit was approaching, and did you verify that you had a basic indeterminate form like 0 over 0? There are only two basic indeterminate forms, 0 over 0 and infinity over infinity. Since I do have one of the indeterminate basic forms, I can apply L'Hopital's rule provided that the numerator is a differentiable function and the denominator is a differentiable function. Since the numerator is a line and the denominator is a parabola, I know I can apply L'Hopital's rule. To indicate that we are applying L'Hopital's rule, we will want to show something in the notation to indicate we've done it. We will use an l'H to indicate we've applied L'Hopital's rule. Without L'Hopital's notation above the equal sign, the two sides will not be equal. They are only equal because of L'Hopital's rule. The l'H is mandatory. Now we apply L'Hopital's rule. L'Hopital's rule says take the derivative of just the numerator. The derivative of x minus a is just 1. Take the derivative of just the denominator, x squared minus a squared, which would be 2x. Remember that a is a constant. Then it says, now plug in a again for x. If I did that, then I would end up with 1 over 2a. In other words, the limit as x approaches a of x minus a divided by x squared minus a squared must be 1 over 2a. Does this match what we would have gotten had we done it with the other method that we learned in Chapter 2? Let's check. In Chapter 2, we would have factored the denominator as the difference of two squares into its conjugate pattern, x minus a, x plus a. Then the common factor of x minus a would cancel. When it cancels, it leaves behind the limit as x approaches a of 1 over x plus a. Then I would take the a and plug it in place of the variable x again, and this would lead to 1 over a plus a, which is 1 over 2a. These answers are precisely the same, which means that L'Hopital's rule did indeed work. You can see that L'Hopital's rule is a bit shorter and simpler to apply, but it does have the condition that the numerator must be a differentiable function and the denominator must be a differentiable function, close to the value a, which is what the limit is approaching. If that is true, then you can apply L'Hopital's rule and take the derivative of just the numerator and divide by the derivative of the denominator. Remember, this works because close to the value, the derivative will look like the tangent line. Again, let's review what L'Hopital's rule says. It says that the limit of the ratio of f to g will be equal to the limit of the ratio of f prime to g prime if f and g are differentiable functions, except maybe at a. Let's look at another example. In this example, we want to find the limit as x approaches 0 of the sine of x minus x divided by x squared. To apply L'Hopital's rule, we must first isolate and look at just the numerator, sine of x minus x. Sine of x is a continuous differentiable function, and negative x is a linear continuous differentiable function. The difference of continuous differentiable functions is also both continuous and differentiable. When we isolate the denominator, x squared, it's polynomial, which is continuous and differentiable everywhere. Thus, L'Hopital's rule applies. First, in order to be able to use L'Hopital's rule, I must have one of the two indeterminate basic forms. There are two basic indeterminate forms for L'Hopital's rule. The indeterminate forms where you can directly apply L'Hopital's rule are 0 divided by 0 and infinity divided by infinity. Now, the infinity divided by infinity is any combination of a positive or negative infinity divided by the other. 0 divided by 0 is the one we're focusing on first. In order to know if L'Hopital's rule applies, I not only need to check differentiability near 0, since that is what the limit value is approaching, but I also need to make sure I have one of these two forms when I plug 0 in place of the variable x. So first we plug in, what is the sine of 0 minus 0 divided by 0 squared? Clearly, the denominator is 0. The sine of 0 is 0, and 0 minus 0 is also 0. Therefore, I do have one of the two basic indeterminate forms. L'Hopital's rule will apply because I have one of the basic indeterminate forms and the numerator and denominator are both differentiable near 0. Now I can apply L'Hopital's rule. I'll put in equals with an L'H over the equals to indicate that I have used L'Hopital's rule. Applying L'Hopital's rule is not taking the derivative. The derivative of a quotient would be f prime g minus g prime f divided by g squared. L'Hopital's rule is not the derivative of the ratio. Instead, L'Hopital's rule is a way of using the linearity of a differentiable function to approximate it near that value. In this case, I'll take the derivative of the numerator. Derivative of sine would give me cosine, and the derivative of minus x would be minus 1, divided by, now I take the derivative of the denominator alone, x squared's derivative is 2x. Once I've taken the derivative of the numerator by itself and the denominator by itself, I've completed L'Hopital's rule. Now I plug the limit value back in again. That means take the 0 and replace the x in both the numerator and denominator with the 0. The cosine of 0 would give me 1. This means I have 1 minus 1 in the numerator, which is 0. In the denominator, I have 2 times 0, which is also 0, which again gives me L'Hopital's rule. The nice thing about L'Hopital's rule is that it can be applied over and over and over again until you get a result. In this case, note that because I have a basic indeterminate form, and because cosine of x minus 1 is differentiable near 0, and 2x is differentiable near 0, I can do L'Hopital's rule again. Applying L'Hopital's rule again, I get that the limit as x approaches 0, well, the derivative of cosine of x would be minus sine x. The derivative of negative 1 is 0, but the derivative of 2x would be 2. This time, there's only one place to plug in the 0, which is here in the negative sine x. This leads to the following result, that limit gives me negative the sine of 0 divided by 2, which is negative 0 over 2, or 0. In other words, the value of this limit is 0. Let's take a look at another example. This is one of those primary trig limits that we learned in Chapter 2 and memorized. You know from what you learned in Chapter 2 that this should come out to be 1. The book went through a very long couple of page derivation using geometry and trigonometry to prove why this limit was 1. However, proving it with L'Hopital's rule is about a 3-line process. In this case, we need to first determine we can use L'Hopital's rule. First, we determine differentiability. Sine of x is differentiable everywhere. X is differentiable everywhere. If I plug in what the limit is approaching, do I get one of my basic indeterminate forms? There are 2 basic indeterminate forms, and I will keep listing them so that you will learn to recognize them instantly. 0 divided by 0, infinity divided by infinity, with any sign combination on the latter one. Let's plug in 0 in place of the variable x in our limit. This would give me the sine of 0 divided by 0, which is 0 over 0, which is one of the basic indeterminate forms. L'Hopital's rule applies, so I indicate that with an L'H over the equal sign. Applying L'Hopital's rule means I take the derivative of the numerator by itself, derivative of sine is cosine, and the derivative of the denominator by itself, derivative of x is 1, and then I plug in the limit value again. When I plug in 0, the cosine of 0 is in fact 1, and I'm done. Let's take a look at another one of the limits that we learned back in Chapter 2. This was the second major trig limit that we learned and memorized in Chapter 2. We know from what we did in Chapter 2 that this should come out to be equal to 0. Let's take a look and see if we can prove that. If we're going to do it, we need to first decide whether or not L'Hopital's rule applies. To do that, we first take the limit, which is approaching 0, and plug 0 in place of the variable x. This gives me 1 minus the cosine of 0 divided by 0. The cosine of 0 is 1, so I get 1 minus 1 over 0, which is one of the two basic indeterminate forms, 0 over 0. Now I check differentiability. Is 1 minus cosine of x differentiable near 0? Yes, in fact, they're differentiable everywhere. Is x differentiable? Yes, it's differentiable everywhere. This means that I can apply L'Hopital's rule. Under L'Hopital's rule, the limit as x approaches 0 of 1 minus the cosine of x divided by x would be equal to the ratio of the derivatives of just the numerator and just the denominator. The derivative of 1 is 0. The derivative of negative cosine would be positive sine of x. The derivative of x is 1. Now I plug in 0 for the variable again. This gives me sine of 0, which is 0. In this way, we can very simply prove the limits that we memorized from Chapter 2. Let's take a look at example 5. In example 5, if I were to plug in 0 for x, I would get tangent of 0 divided by the square root of 0. The tangent of 0 is 0, and the square root of 0 is also 0. So I do have one of the two basic indeterminate forms. Can I use L'Hopital's rule? Tangent of x is not continuous and differentiable everywhere, but it is only discontinuous at odd multiples of pi over 2. That's not near 0, so I'm safe. The square root of x is not defined for negative values of x, but as long as I stay to the right side of 0, it will be both continuous and differentiable. So I can only look coming from the right side of 0. If I do this, then I should be able to apply L'Hopital's rule. But again, this really means that I should be approaching 0 from the right, since the square root of x does not even exist on the left of 0. Now to apply L'Hopital's rule. I put the notation L'H above the equals. Applying L'Hopital's rule means taking the derivative of the numerator by itself. Derivative of tangent is secant squared of x. And then I take the derivative of the square root, which is 1 over 2, the square root of x, times the derivative of x, which is just 1. Now I would want to plug in again. Before I plug in, though, notice that I have secant squared, which is 1 over cosine, and I have a complex fraction in the denominator. Before I do any plugging in, I want to do some algebra to clean this up. I'm going to rewrite this problem then by shifting the secant squared to the denominator as cosine squared of x, and by switching the bottom of the bottom to the top and writing it as 2 square root of x over the cosine squared of x. Now when I plug in the value, I get 2 times the square root of 0 over the cosine of 0 quantity squared. Cosine of 0 is the number 1. This gives me 1 squared for the denominator, or 1. Square root of 0 is 0, and this gives me 0 over 1, which is 0. I'm now done with this limit. Let's take a look at another example. In our next example, we have the ratio of natural log to the polynomial x squared. Let's plug in the limit and see what we have. In this occasion, we have that x is approaching infinity. So our a value is no longer a constant like 0, it is now infinity. In order to know what the natural log of x does as x goes to infinity, I need to visualize what the natural log function looks like. It looks like this. As x goes to infinity, the graph is going to the right. Natural log of x is the y value, and it does very, very slowly go to infinity. This means the numerator goes to infinity. What does x squared look like? X squared is the graph of a parabola with vertex at the origin. Again, as x goes to positive infinity, the y value goes to positive infinity. This gives me the basic indeterminate form, infinity over infinity. To know whether or not you can use L'Hopital's rule for limits that are at infinity, you need to know what the basic graph looks like. Now we're going to see if these are differentiable. Natural log of x is continuous and differentiable everywhere from open 0 to infinity. X squared is continuous and differentiable everywhere. So certainly they're both continuous and differentiable as x goes to infinity. This means I can use L'Hopital's rule. Applying L'Hopital's rule, I take the derivative of just the numerator, natural log of x, to get 1 over x. Then I put a big division bar and take the derivative of just the denominator, x squared, to get 2x. This means I have 1 over x over 2x. You can think of the 2x as over 1 to help you keep straight what goes on top and what goes on the bottom. Remember that the top of the top and the bottom of the bottom are on the top, whereas the middle two, the bottom of the top and the top of the bottom, end up on bottom. In other words, this simplifies algebraically to 1 over 2x squared. Now we can see by playing the Bill Gates rule or some of the other techniques we've learned this semester that as x goes to infinity and the bottom gets larger and larger, the top is a constant, which will drive the whole thing to 0. And that is the value of this limit. Let's compare and contrast the two limits that you see here in example 7. When looking at the one on the left, we have the limit as x approaches 3 of x squared minus 9 divided by x minus 3. In order to apply L'Hopital's rule, I need one of the two basic indeterminate forms. Let's remind ourselves what our two basic forms are. The basic indeterminate forms that you can apply L'Hopital's rule for are 0 divided by 0 or infinity divided by infinity with any sign in any location on the infinities. Now what we're going to do is look at the one on the left. To know what form you have, you first will plug in what the limit is approaching in place of the variable inside the limit. This gives me 3 squared minus 9 divided by 3 minus 3. That is 0 divided by 0, which is an indeterminate form, so I can apply L'Hopital's rule. Applying L'Hopital's rule will lead me to the following. I get the limit as x is approaching 3 of the derivative of the numerator by itself, which is 2x, over the derivative of the denominator by itself, which is 1. Now when I plug 3 in place of x, I get 2 times 3, or 6. The value of that limit is 6. Let's compare that to what we have in the limit on the right. In the limit on the right, I'm going to take the 3 and plug it in place of the variable. This gives me 3 squared minus 9, which is also 0, divided by 3 plus 3, which is 6. This is not one of the two basic indeterminate forms, so I cannot use L'Hopital's rule. However, 0 divided by 6 is the number 0, so I am in fact done already. Let's take a look at another one of the infinity over infinity forms. In this limit in example 8, we see that we have a polynomial divided by a polynomial, and we do also have a limit at infinity because x is approaching infinity. In these cases, we usually apply what we call the Bill Gates rule, which means that as x goes to infinity or negative infinity, only the highest degree terms in the numerator and denominator matter. Let's see if L'Hopital's rule gives us a justification for why this is true. If we were to imply or plug in infinity, and I think about what a cubic looks like as it goes to infinity, I know that a cubic has a basic form that looks something like the following. It may wiggle in the middle, but then it goes up since my leading coefficient is positive. This means as x goes to infinity, the numerator is also going to infinity. Since the denominator is also a cubic with a positive leading coefficient, it also goes to infinity. This is one of the basic indeterminate forms. This means I can directly apply lHopitals rule. If I apply lHopitals rule, then I need to take the derivative of each part of the fraction separately. This is not the derivative of the quotient, because that would invoke the quotient rule. This is instead lHopitals rule. The derivative of the numerator polynomial is 12x squared minus 12x minus 2, all divided by 6x squared plus 2x minus 3, the derivative of the denominator polynomial. When I consider this polynomial divided by this polynomial, notice that this is a quadratic equation with a positive leading coefficient, as is the denominator one. That means that I have some kind of parabola over some kind of parabola. Again, as x goes to infinity, the y value will also go to infinity. This is again infinity over infinity. That means that since these are both polynomials and differentiable everywhere, that I can do L'Hopital's rule again. This leads to the limit as x goes to infinity of the derivative of the numerator, 24x minus 12, divided by the derivative of the denominator, 12x plus 2. Now the numerator is a line, as is the denominator. This is a line which slopes up with a slope of 24. When I think about it, as x goes to infinity, the y value goes to infinity, as does this line. This is again the form infinity over infinity. Since lines are differentiable and continuous everywhere, I can do L'Hopital's rule again. This leads me to the limit as x approaches infinity of 24 divided by 12. When I reduce 24 divided by 12, I get 2, and the limit of the constant is the constant itself. Notice that this number is equal to the ratio of the leading coefficients. In other words, L'Hopital's rule is the reason the Bill Gates rule works. In the next short video, we'll look at the next two indeterminate forms, which are arithmetic in basis. Then we'll look at the 3 power indeterminate forms. There are 7 indeterminate forms in all. You can close this video now and take a break, but then you will need to watch the next video on the arithmetic indeterminate forms.